when we have identified tasks that can be worked on in parallel, the next thing is to decide how the tasks should be given to different threads. And there are two main options. One is to do it statically, meaning that we decide either at compile time or at the beginning of the program which task should do what. Sorry, which thread should do which tasks. For some algorithms that is suitable. For instance, matrix multiplication. It's easy to say which thread should compute which part. Okay, but for other algorithms it's not so easy, because it will lead to load imbalance. In preflow push, if we would divide as follows, that we simply take all the nodes and give an equal number of nodes to each thread, and assuming that we say the computing of for one node is the task. Okay, then if the action in the preflow push algorithm does not involve some parts of the graph, then this is a wasted effort. I mean, it will be load imbalance that is completely unnecessary. And what is actually happening in the graph is typically known during the execution. So one approach is to have a central shared work queue with the nodes that want to do push or relabel, I mean active nodes. So we can have a work queue with active nodes, and if we let each thread take one such task, meaning one node, with excess preflow, and work on that, then we have a dynamic assignment. So this will give the best load balance. But with one shared work queue, that work queue must be protected when the threads take a node from it. So it may be better to have separate work queues, one for each thread, and occasionally divide the work in a fair way. When one thread has nothing to do, it may want, I mean, then, and some other thread has lot of things to do, then they should split the work queues in some way, possibly. So this is an interesting question. How should the tasks be assigned to the different threads? And here is a trade-off, another trade-off, namely, we can easily spend too much time on partitioning the graph so that each thread has a useful set of nodes to work on. So what we must do is to find a simple technique, sufficiently simple so that it works well, but does not take too much time, because partitioning the nodes is just overhead. It's just a waste of time in some sense. Okay, so you will find this quite interesting, I'm sure. Okay, again to note is that decomposition, and decomposition meaning dividing into parallel tasks, and assignment, assigning tasks to threads. This is called partitioning, and this is an algorithmic step in the parallelization. And hopefully we can do that without taking too much of the details of the machine into account. This works for different languages as well. And for Akka and Scala, we had the extreme version of one actor per node. And of course, when running the akka program, it's not one thread per node, but it's divided during the runtime. But that's from the view of the programmer, it's one activity per node. So that's the easiest way to get the load balance. Okay, orchestration. That is when we write the source code. Okay, so what do we have to do? We have to consider if we want to use message passing or shared memory, and what can we do with our data structures in order to reduce the number of cache misses, to reduce the cost of communication and synchronization, meaning it's better if one thread that is typically one CPU and parts of the cache works on the same data and not giving a node to different CPUs, because then the data has to be copied. Okay, and we want to reduce the synchronization, the need for synchronization. One example of that is to have private work queues instead of one common work queue. Okay, so and here we will affect the performance to a large degree. So we want to avoid synchronization, but of course we need synchronization for correctness. Okay, and so we want to reduce the number of things which must be done by one thread at a time, and we want to do work so that we get on the right track as quickly as possible. Think of the preflow push. The first thing that happens is that the source pushes to its neighbors, but what should those neighbors push to? Okay, mapping. Well, as I mentioned, we usually cannot do that manually, but it is the operating system which decides which thread should be at which CPU. So, but if we can control it, it's usually called to pin a thread to a certain CPU. But since usually our program runs on a machine which also does other computations, it may not be the best idea to try to use this. Okay, a good rule in partitioning an algorithm and the data that is computed on is to say that one thread owns a certain part of the data, at least for some time, and then the other threads will read that data but not modify it. So this rule is called owner computes, and it usually helps to think in this way, to identify which one certain thread that owns the data. Okay. What we will do next is to look at the development of parallel computers.